Good afternoon, everyone, and welcome to the next session for the novel technologies for food processing and shelf life extension. So, this is the Saturday session that has been preponed to the Friday just for this week alone. From next week onwards, we'll still proceed with the Saturday session itself. So, in this particular problem solving session, we will be dealing with problems related to week 6 syllabus. And in case if you guys have any doubts, you can mail me or you can post it in the discussion forum in the NPTEL portal, and we can take it up in the next class as well. Moving to question 1. Match the pair of food products in column 1 with its pH in column 2. So in column 1 you have 3 different food products, which is tomato, milk and apple. In column 2 you have less than pH less than 4, 4 to 5 and pH greater than 5. So as you can see here, the three food products are related to a pH less than that of the neutral, and this is because these food products contain organic acids that result in a slightly lower or an acidic pH of these food products. So we look at why each of these food products has an acidic pH and what is the pH value as well. So in case of tomato, the pH ranges from 4.3 to 4.9 due to the presence of organic acids such as malic acid, citric acid, ascorbic acid and folic acid. So it's majorly that these 4 acids contribute to the acidic range of the tomato, and pH of the tomato is often found to be an indicator of how ripe the tomato is. So generally it's the ripe tomato that has this low acidic pH of 4.3 to 4.9, and this pH will give an indicator of how ripe the tomato is. So the pH of tomato ranges from 4.3 to 4.9, which is the second option. So in case of milk, as you guys would already know, milk contains lactic acid due to lactic acid bacteria as well. So the lactic acid results in a pH of the milk being slightly lower than that of the neutral pH. So it will be somewhere around 6.7 to 6.9. It will only be slightly lower than the pH 7 or the neutral pH. So for milk, due to the presence of lactic acid, it has a pH above 5, generally in the range of 6.7 to 6.9. And the apple, which is apple has a pH less than that of 4, and this is because of the presence of malic acid and ascorbic acid. It is generally ranges between 3.3 to 3.9. So the pH of apple is less than that of 4. So tomato has a pH of 4 to 5, milk has greater than 5, and apple has less than 4. So the answer to this question is option C. 1 is with 2, second row is with the third option, and third row is with the first option. Moving to question 2, so we'll be dealing with 2 numericals in this session. So the first numerical, the tomato juice is flowing at a flow rate of 1.7 meter cube per hour through a holding tube in an aseptic processing system. The holding tube has an inside diameter of 4.35 centimeter and the flow is laminar. The residence time of the food in the tube is 2.5 minutes. So calculate the length of the holding tube. So in case of an aseptic processing system, what often happens is that we either sterilize the food separately and the container separately and then put the food inside the container, or we place the food inside the container and all together sterilize the entire container along with the food. So both of these can happen. In this case, it is the food that is getting separately sterilized. In this case, you will have food passing through a holding tube where it will be subjected to very high temperatures, and at this high temperature and for a specific amount of time, this will be enough to kill all the pathogenic microorganisms and hence increase the shelf life of the product as well. So in this case, the tomato juice is passed through a holding tube where you will have a high temperature, and this is happening at a rate of 1.7 meter cube per hour. The diameter is given of the holding tube, and it is mentioned that the flow is laminar. And it is also mentioned that the residence time of the food in the tube is 2.5 minutes. So when you mean the residence time, it is the amount of time a particular fluid particle spends inside let's say a container, let's say in this case it's a holding tube. So the amount of time it spends inside the holding tube is 2.5 minutes. So we need to calculate what is the length of the holding tube. So given is the Q, which is the flow rate, which is 1.7 meter cube per hour, D, which is the inside diameter, which is 4.35 centimeters, and T, that is the residence time, is 2.5 minutes. So we need to calculate the length of the holding tube. So that can be done by the formula. Length of the holding tube is equal to V max, which is the maximum velocity possible in that tomato juice flow, into the residence time. So here what is given is that it's an average rate that is given. If nothing is mentioned about being the maximum rate, it generally means that it's an average flow rate. So when you divide average flow rate to calculate the velocity, what you get is the average velocity and not the maximum velocity. So from average velocity, we'll have to calculate the maximum velocity and then proceed with the concept. So from flow rate, it is easy to calculate the velocity of a fluid if you know what is the diameter of the cross-sectional area through which it is flowing. So V is equal to Q by A, where Q stands for the flow rate of the fluid, where A stands for the cross-sectional area through which the fluid is flowing. So Q, since we are dealing with a cylindrical pipe here and the diameter is given as 4.35 centimeters, so the cross-sectional area will be the circular region through which the liquid is flowing. So the cross-sectional area of a circle can be given by pi d square by 4. So Q divided by pi d square by 4 will give you the velocity, that is the average velocity of the tomato juice. So we have Q, we have D here, all we need is to substitute it in the equation. And when we substitute it in the equation, we have 1.7 meter cube per hour divided by pi into 0.0435 the whole square divided by 4. So this will give us a velocity of 19.07 meters per minute. So if you simplify this equation, you will get 19.07 meters per minute. So with this velocity, this is the average velocity, and we need to find out what is the maximum velocity. So for different kinds of fluid flow, there are different ways of calculating the maximum velocity from the average velocity. So in case of a laminar flow, your maximum velocity is equal to 2 times the average velocity. Whereas in case of turbulent flow, it will be 1.25 times that of the average velocity. So depending upon the flow that is mentioned in the question, you need to calculate the maximum velocity based on that. So for a laminar flow, V max is equal to 2 into V average. So V average is what we've got here, and from that we can calculate the V max. So V max is 2 into 19.07 meters per minute. So V max is 38.14 meter per minute. So now we have the maximum velocity of the fluid particle possible inside that holding tube. Now we have the Vmax. We already know what is the residence time in the question. From there, you can calculate the length of the holding tube. So as I mentioned, the length of the holding tube is equal to Vmax into the residence time. Now by direct substitution, we have 38.14 meter per minute into 2.5 minutes, which will give you the length of the holding tube as 95.35 meters. So the answer to this question is option C. Hope this is clear. In case you guys have any doubts, you can mail me back or post it in the discussion forum. Moving to question 3. The initial concentration of ascorbic acid in an aseptically packed lemon juice is 90 mg per 100 grams, and the final concentration after storage of 150 days is 70 mg per 100 grams. The loss of ascorbic acid follows first order kinetics with a rate constant of 0.00542 day inverse and the activation energy of 70,110 joule per mole at room temperature. Calculate the storage temperature in degrees Celsius. Assume that the value of R is 8.314 joule per mole Kelvin. So here you can see that even if you even during storage, you can often find that some of your food products get degraded or follows some kind of a decay. So in this case here, you can see that initially when you packed the lemon juice, you had an ascorbic acid of 90 mg per 100 grams, and then during storage for 150 days, the final concentration goes down to 70 mg per 100 grams. But what we need to find out is that we do not know at what temperature is the storage happening. That is, what is our storage temperature. That is what we need to calculate. But what is given is that it follows first order kinetics and the rate constant is given. The activation energy is given, and this rate constant is at 25 degrees Celsius as mentioned here. So given that ascorbic acid decay follows first order kinetics, your rate will be directly proportional to the concentration of ascorbic acid present. That is, dC by dt will be directly proportional to C. And when you take out the proportionality, you will have a proportionality constant coming in. So dC by dt will now be equal to minus Kc. Here, the negative sign stands for the fact that the amount of ascorbic acid decreases with time. So because of this decrease, you have a negative sign here. Had it been a kind of an increase also, you will have a plus Kc. But here, since the ascorbic acid is decaying over time, you have minus Kc here. So since it follows first order kinetics, it is dC by dt is directly proportional to C, and when you remove the proportionality sign, you will have equal to minus Kc, minus because it follows a decay. So now when you take C on this side and you integrate, you have dC by C ranging from C0 to C equal to minus K of dt integrating from 0 to T. Here C0 is the initial concentration of the ascorbic acid present. C is the final concentration present after some time, say T, is equal to minus K 0 to T dt. So now when you integrate this, you have ln of C by C0 is equal to minus Kt. Here again C stands for the final concentration. C0 stands for the initial concentration of the ascorbic acid. So this is not just for ascorbic acid. When you have any component, be it microbial organism, or you have a vitamin, or you have any food product that follows a first order decay kinetics, this is one equation that you can use, and this was also discussed in the first week and the second week lectures as well. So if you guys have any doubts, you can refer back to those sessions as well. So ln C by C0 is equal to minus Kt. So now you have C0 given as 90 mg per 100 grams. You have time given as 150 days. And you have C given as 70 mg per 100 grams. From there, we can calculate what is the K. So this is just a given in the question. C0 is 90 mg per 100 grams. C is 70 mg per 100 grams. Time is 150 days. Activation energy is 70,110 joule per mole. And at 298 Kelvin, the rate constant is given as 0.00542 day inverse. The reason why we are calculating K again here is that we do not know what the storage temperature is. And the rate constant highly depends upon the temperature. So the rate constant at 25 degrees will not be the same as the rate constant at 4 degrees. So at every temperature, since the K is changing, you need to calculate what is the K at the storage temperature, which we still don't know yet. So in order to calculate K, we are substituting all the other known. So ln 70 by 100, which is your C, divided by 90 by 100, which is your C0, is equal to minus K into 150. So from this, you can calculate K, which comes out to be 0.00167 day inverse. So this is the rate constant of decay at the storage temperature. So now, generally, all the rate equations, specifically when they follow the first order kinetics, happen to also follow what is known as the Arrhenius equation. The dependence of rate constant on temperature follows Arrhenius equation. This was again one of the concepts that was taught in week 1 session, problem solving session. If you guys have any doubts, you can refer back to those lectures as well. So the dependence of rate constant on temperature follows the Arrhenius equation, and Arrhenius equation can be given by this, given here below. K is equal to A e power minus EA by RT. So A is a constant, EA is the activation energy, R is the universal gas constant, and T is the temperature. So here you can see the rate constant actually depends upon temperature. So as your temperature changes, your rate constant will also change. So what we do is, in order to find out, so we know at the storage temperature what is K. So all we need to find out is T. But we don't know what is A. So uh, in order to simplify things further and not calculate A, we have another method to move forward with this. That is, if you already know what is the rate constant at one temperature, any temperature, you can always calculate what is the rate constant or the temperature at a different condition. So in order to make these things more clear, what you do is you take a logarithm on both the sides. So ln k will be equal to ln of a e power minus ea by rt, and when you simplify that, you'll have ln a minus ea by rt. So if you take a logarithm on both the sides, this is what you'll get. Ln k is equal to ln of this entire term, and if you simplify that more, you'll get ln a minus ea by rt. So if you have already at a particular T1, you already have a K1, that can be given as ln K1 is equal to ln A minus EA by RT1. So since A is a constant, that will not depend upon temperature. A is fixed for a particular kind of a food product that you are dealing with. Okay, so if you know what is the rate constant at one temperature, you can calculate what's the rate constant at a different temperature. So as I was explaining, so for one condition, let's say the first condition, you have ln k1 is equal to ln a minus ea by rt1. A being constant will remain the same throughout for a particular food product. So for the second condition, say condition 2, you will have ln k2 is equal to ln a minus ea by rt2. So you have two conditions here. In order to eliminate the use of A, what you do is you subtract this equation from this equation. So you have ln k1 minus ln k2 is equal to ln A minus EA by RT1 minus ln A plus EA by RT2. So ln A minus ln A gets cancelled. So now you will have an equation devoid of the constant A, and you can directly substitute the values if you have the rate constant at a different temperature. So in this case, if you simplify this further, so this will become ln k1 by k2, and you will have minus ea by r t1, ea by r 1 by t1 minus 1 by t2. So that is what you have. On simplifying, you have ln k1 by k2, ln a gets cancelled. So you will have minus ea by r into 1 by T1 minus 1 by T2. So in this particular question, we already know what is T1 and what is K1. That is at 298 Kelvin, the rate constant is already given. And at some other temperature, that is the storage temperature, we have just calculated what is K2. That is what we calculated in this particular step. So this is at the storage temperature. This is at 298 Kelvin. So you have T1, you have K1, you have K2, you need to find out what is T2. So that is the question asked. By direct substitution, at 298 Kelvin, K is 0.00542. Let that be T2 and this be K2. So at some unknown T, let's say T1, your K1 is given as 0.00167, which is what we calculated. So by substituting these, ln 0.00167, which is your K1, divided by 0.00542, which is your K2, is equal to your EA is given. So your activation constant and A will remain constant for a particular food product. So that will not depend upon temperature. So your A and EA will not depend upon temperature. It is only your rate constant that will depend upon temperature. So EA can be considered as constant, which is equal to 70,110 as per given in the question. R is 8.314 joules per mole Kelvin. And T1 is what we need to find out, which is the storage temperature, and T2 is 298 Kelvin. So on simplifying further, you get minus 1.1772 is equal to minus 70,110 divided by 8.314 into 1 by T1 minus 1 by T2. So here you can see your T1 and T2 should always be in Kelvin and not in degrees Celsius. So while substituting in this equation, you need to make sure that your units are consistent. So from this, you can calculate T1 to be 286.09 Kelvin or 12.94 degrees Celsius. Hence, the answer is option B. So here, as you saw, we saw that your food product decay in either the storage temperature or any other normal processes generally follow a first order kinetics. So you can use the same equation for all the food products that follow first order kinetics, and then all the rate constants are generally found to follow Arrhenius equation at least in a certain temperature range. So when it follows an Arrhenius equation, you can use this formula to calculate what is the K at a different temperature. So hope this is clear. So moving on to question 4. Match the food antimicrobials in column A with the natural sources in column B. So first is acetic acid, propionic acid, sorbic acid, and fourth lactic acid. And on the other side you have yogurt, rowan berries, vinegar, as well as Swiss cheese. So any clue what the answer is? Some of them would be easy to guess. So if you guys have any doubts or any answers that you would like to answer, you can either unmute yourself or you can post it in the discussion, the in-call messages as well. So what is straightforward, we all know that acetic acid is something that is very commonly found in vinegar. So vinegar is one of the most abundant natural sources for acetic acid. So acetic acid stands for goes with vinegar. Then uh, then is propionic acid. So propionic acid 2D, yeah, 3 is, yeah, so the answer is B. So propionic acid is found in Swiss cheese, and this propionic acid is due to the presence of Propionibacterium fronteraceae. This is one of the bacterial species that are present in the Swiss cheese that helps in the production of propionic acid in the Swiss cheese. And third is sorbic acid, which is found in berries and other fruits. And one of the example of the berries is rowan berries. And fourth is the lactic acid, which is found in yogurt. So the answer is option B. Moving on to question 5. Dash is an antimicrobial, a primary iron binding compound which is naturally present in milk and colostrum. So you have A, lactalbumin, B, lactoferrin, C, lactose, and D, lactate. So yeah, the answer is lactoferrin. So is uh, um, lactoferrin is an antimicrobial compound that is present in milk and colostrum. So this comes under your animal sources of antimicrobial compounds. And lactoferrin has two iron binding sites that will all sequester the iron, and hence the bacteria will not have any iron molecules to survive anymore. So iron is important for the survival of the bacteria as well. And so when you start sequestering iron, this will impede the growth of microorganisms as well. So lactoferrin is the antimicrobial that is involved, that is present in the milk and colostrum. Lactalbumin controls the amount of lactose that is present in the milk. Lactose is a sugar. It's not an antimicrobial. Lactose is just a sugar, and lactate is basically your lactic acid. Lactate is basically your lactic acid that is present in milk and curd. So the answer is option B. Moving to question 6. Dash is the enzyme that catalyzes the hydrolysis of beta 1 to 4 glycosidic bonds between N-acetylmuramic acid, which is NAM, and N-acetyl glycosamine, which is NAG of the bacterial cell. So you have N-acetylmuramide glycan hydrolase, which is one of the enzyme, lysozyme, both A and B, and D is trypsin. So which one of these enzymes catalyzes the glycosidic bonds between NAG and NAM? So it's both A as well as B. So lysozyme is also known as N-acetyl-muramide glycan hydrolase. That is an enzyme that catalyzes the beta 1 to 4 glycosidic bonds between NAM and NAG of the bacterial cell walls. So these NAM and NAG are basically like the building blocks of the bacterial cell wall, and if and the cross linking between them is important for the intact nature of the bacterial cell wall. So if this cross linking is disrupted, the bacterial cell wall is also disrupted, and hence lysozyme is often acting as an antimicrobial enzyme that can be exploited in food processing. So lysozyme is also known as N-acetyl-muramide glycan hydrolase that catalyzes the bonds between the NAG and NAM and hence disrupting the bacterial cell wall. So this lysozyme is present in eggs, milk, tears, insects, and insects, fish, and other secretions. And how this is processed is that lysozyme is present in a hypotonic solution, and this causes the lysis of the bacterial cell walls. So apart from breaking open the NAG and NAM, if you put your cells in a hypotonic solution, because of the pores or the the weaker cell wall, often what happens is that you will have a change in osmolarity. That is, all the water will start coming inside the cells, and because of a weak cell wall, your cells will start rupturing and breaking. Your cells will swell up and then will rupture and break, which is why it is often preferred to use lysozymes in a hypotonic solution to cause lysis of the bacterial cells. So the lysozyme will weaken the bacterial cell wall. The hypotonic solution will help in swelling of the bacteria and then lysis of the bacterial cells as well. And the other option, trypsin, is actually a serine protease that is secreted as a part of digestion in animals. So that is not involved in the bacterial cell wall disruption. Only lysozyme or the N-acetyl-muramide glycan hydrolase is involved in as an antimicrobial enzyme. The answer is option C. Moving to question 7. Hurdle technology is a combined method technology for food preservation where combination factors act A. antagonistically, B. symbiotically, C. synergistically, and D. all of the above. So what could be the answer for this? So before we proceed, any clue what is a hurdle technology? So all these in the previous week sessions, we were all looking at high pressure processing, sterilization and stuff. In all these cases, there was only one factor acting against the microbes to help in food preservation. Whereas in case of hurdle technology, you will have multiple factors acting together to help in a better efficiency of food preservation. That is, in case if you are using temperature as a method to help in food preservation, you will have to end up heating the food product to extremely high temperatures, let's say around 121 degrees Celsius or so. But in case if you are using hurdle technology where you are using a combination of temperature, pH, water activity and so on, the extremity to which you will have to change the factors is not that bad. So instead of heating to 121 degrees Celsius, you can just mildly heat the food, and on top of the mild heating, you can further add in other factors like changes in pH, changes in salt. So all these factors will come together and will prevent the microbes from sustaining. So as you can see here, each of these factors that you will be changing will act like a hurdle to your microorganisms. So by the time, so at each and every hurdle, the amount of microorganisms that are surviving will be keep on reducing. So at the first hurdle, let's say you have 100 microorganisms. After the first hurdle, you will have, let's say, somewhere around 70. After the second hurdle, you will have somewhere around 50. So on and so forth. With each and every hurdle, the number of microorganism count will also keep reducing, and the extreme or the condition at which you need to maintain the food will also not be extreme. It will be only slightly milder when compared to using only one factor. So hurdle technology basically uses a combined factors or combined method where you use multiple factors to metabolically exhaust the microorganisms. So by the time you reach the final hurdle, microorganisms will all be exhausted after crossing so many hurdles that it will no longer be viable, or it will no longer be a threat to your food. So by this time, by the last hurdle, your microorganisms will be metabolically inactive or exhausted. And then when you have your final step, like say adding preservatives or so, you will be able to sustain the food for a longer time, that is, it will have a longer shelf life. That is why hurdle technology is one of the new upcoming technology, where you'll have multiple methods coming in. So apart from the fact that you have to use less extreme conditions, one other effect is that often these conditions can come together and act synergistically. So that is one of the main advantages of using hurdle technology. So when synergistic parts come together, they can accomplish more than what they could do alone. So one of the example is the use of hydrogen peroxide. So hydrogen peroxide is one of the commonly used compounds for antimicrobial activity. So when you use hydrogen peroxide alone, it does not work that well. But at the same time, if you use hydrogen peroxide with very high temperatures, it will be able to have a better efficiency of killing microorganisms. So as you can see here, combination factors can often help in more efficient killing of the microorganisms, and these act synergistically to produce that effect. So the answer is option C. I hope this is clear what the meaning of hurdle technology is. That is, you'll have multiple hurdles, then finally end up storing the product, and this will have a better shelf life than the food product that where you have used only one factor. And uh, one of the other advantages of using a hurdle technology is that now, since you're using lesser extreme conditions or so, your cost of production will decrease and you'll have a lot of energy savings as well. So this is one other advantage of using a hurdle technology. Moving to question 8. In osmodehydrofreezing technology, the food material is subjected to osmotic dehydration followed by dash and then freezing processes. So you have A, combined method, B, cooling, C, air dehydration, and D, concentration. So the name itself suggests the osmodehydrofreezing technology. So what is the second step after osmotic dehydration? So this osmodehydrofreezing is one of the it's one of the examples of a hurdle technology where you have multiple factors coming in. So as the name suggests, you have osmotic dehydration, then you'll also have air dehydration, and then you'll have freezing. So there are three different processes that are combined together in this particular hurdle technology. So what happens is that it's a combined process in which osmotic dehydration is followed by air dehydration and freezing. Uh, and this is used as an alternative for drying by hot air only. So, in this method, our main goal is to reduce the water activity. That is, if a specific amount of water or moisture is present inside the food, this will enable the growth of microorganisms. But if you start drying or if you start removing the water activity in the food, uh, by removing the water activity and the moisture, you will uh, cause a stress to the microorganisms, and this will arrest the growth of microorganisms in food. So the main idea behind this particular osmodehydrofreezing is to remove any moisture content or to reduce the water activity in foods. The answer is option C. So in osmotic dehydration, by putting it in a hypertonic solution, by putting the food in a hypertonic solution or so, you will be able to remove all the water from the cells, and on top of that, you will be using air dehydration by hot air or so. This will further remove the water, and then by freezing, you are freezing all the water molecules that are available for the microorganisms to grow. So if you freeze the water molecules, it will no longer be available for the microorganisms, and hence you will extend the shelf life of the food product. Any doubts so far? Okay, moving to question 9. Which of the following is not a principle or objective of hurdle technology? So, A, you have direct killing of microbial spores. B, affecting the microbial stability by interaction of several factors. C, preventing the multiplication of microorganisms. And D, disturbing the homeostasis of microorganisms. So which one of these is not a principle or objective of hurdle technology? Okay, so as we discussed in the hurdle technology, you'll have multiple hurdles at the end of which microorganisms are now metabolically exhausted. So what happens is that you are having multiple factors coming into picture. So B is correct, affecting the microbial stability by interaction of several factors. So several factors will synergistically affect the microbial stability, and at the end of the hurdles your microbes will be metabolically exhausted, and hence it might not you might not kill the microorganisms, that is also possible, but you might not sometimes kill the microorganisms. It will just be metabolically exhausted, that it will no longer be able to multiply. So preventing the multiplication of microorganisms is one of the principle of hurdle technology as well. That is, it becomes metabolically exhausted, need not necessarily kill the microorganisms, but it will definitely prevent the multiplication of it. And D is disturbing the homeostasis of microorganisms. So if you have so many factors coming into picture and so many of them acting in a synergistic way, homeostasis, that is the ability of the microorganisms to regulate its inner environment to an optimum condition, will be disturbed. So if you have so many changes happening in the environment, this will disturb the homeostasis or the regulation of the inner cellular environment, and this disturbing the homeostasis is also one of the principle of hurdle technology. The principle involves the use of preservative factors or hurdles that disturb the homeostasis of the microorganisms. Microorganisms are not able to jump over all the hurdles present in the food product, and the preservative factors prevent the microorganisms from multiplying and causing them to remain inactive or even die. So the hurdle concept illustrates the complex interaction of the temperature, water activity, pH, etc. that significantly affect the microbial stability. So in this case, we do not generally involve direct killing of the spores. We are just inactivating the spores, or inactivating the microorganisms to as much extent as possible. Direct killing is generally possible only if you use extremely high temperatures, like such say in case of an autoclaving or so, where you have a temperature of 121 degrees Celsius and a very high pressure. That is when you will often have killing of the spores. When you're using milder conditions, like in the say of hurdle technology, where you have milder temperature conditions and so on and so forth, because of these milder conditions, killing of the microbial spores is no longer possible. So that is not the principal objective. It is just to completely inactivate the spores, or to help the spores germinate and then kill or then inactivate the microorganisms. That is what is possible in a hurdle technology. So the answer is option A. Hope this is clear as to why direct killing is not possible. Because first thing is that killing is not something that often happens in hurdle technology. It is more of inactivation that happens. And second thing is that for killing of the spores, you require very high temperatures, and often in hurdle technology, you use milder conditions but a lot more conditions. Like you will have 5 factors coming in with milder conditions instead of one single factor at an extreme condition. That is what happens in a hurdle technology. So answer A is, option A is incorrect or not the principle of hurdle technology. Moving to question 10. Which of the following statement is not true for triglycerides of animal sources? A. It is more prone to hydrolytic than oxidative rancidity. B. It is a soft solid at room temperature. C. It has high unsaturated fatty acid contents and undergoes hydrolytic rancidity rarely. And D. It has higher Reichert micelle number. So any clue what the answer is? before we proceed further, any idea what a Reichert-Meisel number is? So a Reichert-Meisel number is a measure of the volatile soluble fatty acids. Basically, it tells you how much amount of soluble volatile fatty acids that are present in your particular food product. That is defined as the number of milliliters of zero point 0.1 normal alkali required to neutralize the soluble fatty acids contained in 5 grams of fat. So this is how you calculate a Reichert-Meisel number of a particular fat product. So you have 5 grams of fat, and you'll add how much ever amount of 0.1 normal alkali you add will be an indicator of how much amount of volatile soluble fatty acids are present. So, so this is what is Reichert-Meisel number. So any clue what is a triglyceride? So this has been discussed in the last lecture of week 6, the different kinds of lipids that are involved. So any clue what a triglyceride is? So in a triglyceride is a form of a lipid where you have a glycerol backbone, and then one of the hydroxyl residue of the glycerol is esterified to an acyl residue. So you have three different hydroxyl groups present in glycerol molecule. So in a triglyceride, we'll have all the three hydroxyl groups replaced by an acyl residue. That is, let's say if you have only one hydroxyl group replaced, it is known as a monoglyceride. If you have two hydroxyl groups replaced, it is known as diglycerides. And if you have three replaced, you have triglycerides. So in all these mono, di and triglycerides, you will have a glycerol backbone that is common. The only thing that will be different is the kind of the acyl residue and the location of the hydroxyl group where it has been substituted or esterified. So that is the triglyceride. And when you have animal sources, triglycerides from animal sources are generally known as fat, whereas that from plant sources are known as oils. So that is the difference between triglycerides from animal source. The first difference between triglycerides from animal source is that it is called a fat, and triglycerides from plant sources is known as oil. So we look at each and every properties of the triglycerides from the animal source. Yes, it is more prone to hydrolytic rancidity than the oxidative rancidity, which results in the production of free fatty acids. The other thing is that fats or the triglycerides from animal sources are rich in saturated fatty acids. It is not rich in unsaturated fatty acids. It is rich in saturated fatty acids, and these fats are solid. They are soft solid at room temperature. They have less iodine number. So iodine number is indicative of how many unsaturated bonds are present in the fatty acids. So lesser the iodine number, lesser is the number of unsaturated lesser the number of double bonds present in the oil or the fat. So less iodine number stands for lesser double bonds. So since we are dealing with saturated fatty acids, animal fats will have less iodine number, higher Reichert-Meisel, that is it will have higher number of volatile soluble fatty acids. So in contrast, plant triglycerides, also known as oil, are relatively rich in unsaturated fatty acid content. They are liquid at room temperatures. They have high iodine number and relatively lower Reichert-Meisel number. So you can see animal fats and plant oils are completely different from one another. So in order to brush up your knowledge on what is a saturated fatty acids will have all the carbon bonds satisfied. That is, everything will have only a single bond. Whereas in case of unsaturated fatty acids, you will have double bonds in the chain. So depending upon how many double bonds you have, they can either be monounsaturated fatty acids or they can be polyunsaturated fatty acids. That is, if you have one double bond, it is a monounsaturated fatty acid. If you have multiple double bonds in the same molecule, then it is known as polyunsaturated fatty acids. So iodine number will tell you how many double bonds are there. So if you have less iodine number, it means it has lesser double bonds, which again means that it is rich in saturated fatty acids. So the main statement that's not true about the triglycerides of animal sources is that it has a high saturated fatty acid content and undergoes hydrolytic rancidity rather than oxidative rancidity. So statement C is false. This holds true for plant sources and not for animal sources. Hope this is clear. Is there any confusion? So animal sources are solid at room temperature. They are saturated fatty acids. They undergo hydrolytic rancidity. They have less iodine number and higher Reichert Micelle number. It is the exact opposite for plants. Plants will have rich in unsaturated fatty acids. It will be liquid at room temperature. It will have a high iodine number and low Reichert Micelle number. So hope this is clear. Any doubt? Okay, move on to question 11. Match the vitamins with their chemical names. You have vitamin A, D3, E, K1 and K2, and the names are tocopherol, menaquinone, phyloquinone, cholecalciferol and retinol. So can you match which one of these vitamins correspond to what names? So C1 stands for 5. Yeah, vitamin A stands for retinol. Vitamin D3 stands for cholecalciferol. Vitamin E for tocopherol. Vitamin K1 for phyloquinone. And K2 for menaquinone. So what is common amongst all these vitamins is that they are all fat soluble vitamins. So that is one common feature of all the vitamins that is given here. So these are all fat soluble vitamins. Moving to question 12. So this is a combined question where you'll have a single case and then you'll have multiple questions. So the paragraph is as follows. People in India are known for implementing traditional home remedies. One such example is the extensive use of turmeric or curcuma longa powder in cuisines and also for application on fresh cuts or wounds. So curcuminoids is a family of compounds found in curcuma longa which have antimicrobial properties. Curcumin, which accounts for approximately 3% by weight of turmeric powder, is an important member of the curcuminoids. And curcumin, along with the other members like D-methoxycurcumin and bis-methoxycurcumin, have been shown to possess antimicrobial activity. So this is just a background on turmeric and its antimicrobial compounds that are present inside turmeric. So a scientist conducted several experiments to check the antimicrobial potential of turmeric on different microorganisms using MIC, which is the minimum inhibitory concentration assay. Taking into consideration that the scientists assumed that only curcumin in the turmeric powder had antimicrobial effect, answer the following questions based on the research carried out by the scientist. So we look at each and every question one by one. So basically we are looking at the MIC of curcumin over multiple organisms. And based on that we'll have questions. So question 12. Based on the MIC depicted for various microorganisms in the bar graph, select which ones are the most sensitive and which one is most resistant to curcumin respectively. So before we go ahead, do you any clue what MIC is? What is the definition of MIC or minimum inhibitory concentration? This is something that was also discussed in the assignment question of this week as well. So minimum inhibitory concentration is the minimum concentration of the drug or any compound that prevents the visible growth of bacteria. There might be still growth, but then it will prevent the visible growth of bacteria. So the minimum concentration of the drug required is known as MIC. So lower the MIC, you can either say more potent is the drug or more sensitive is the bacteria to that drug. It can be either ways. So lower the MIC, more potent is the drug against that particular bacteria, which means that that bacteria is sensitive. Higher the MIC, you will have more resistant bacteria because you will require very high dose to prevent the growth of bacteria. So low MIC means lesser resistance and high MIC means higher resistance to that particular compound. So from in this case, which of the organisms is the most sensitive and the most resistant? So here you can see Staphylococcus aureus has basically very minimal MIC. Here in the y-axis you have minimum inhibitory concentration. In the x-axis you have different organisms against which curcumin is tested. So here you can see Staphylococcus aureus has almost minimal MIC, which means it requires very tiny concentration of the drug to prevent its growth. And this in turn means that Staphylococcus aureus is extremely sensitive to curcumin, which is why a very small concentration was enough to prevent its growth. So the most sensitive in this particular set of organisms is the Staph aureus. And when you compare which is the most resistant, you have two organisms. You have Agalactiae and you have the E. tarda as well. So both of these have very high MIC concentrations among the rest, and hence these two can be considered as the most resistant. So among these options here, Staph aureus is the most sensitive and Agalactiae is the most resistant. So the answer is option A. Staph aureus has negligible MIC reflecting the higher sensitivity. On this similar lines, Agalactiae and E. tarda are most resistant because of highest MIC. So the answer is option A. Hope this is clear, the concept of MIC. All the rest of the questions are also kind of somewhat dependent on the concept of MIC as well. So moving to question 13, a similar study. The scientist now conducts experiment to obtain the extracts from the turmeric powder using solvent extraction, a commonly used technique in the food industry to obtain compounds with the desired properties. He used ethanol and hexane as solvents to obtain two different extracts. Now, based on the experiment result as shown in figure 2 and 3 below, which of the following two extracts do you think are more potent to A. hydrophila? So this particular figure is for only ethanol extract. I will show you another figure for hexane extract. So you have two different graphs, one for the ethanol extracted turmeric and other graph is for hexane extracted turmeric, which I will show you in the next slide. So we will first calculate what is the MIC for A. hydrophila of turmeric against A. hydrophila. So amongst these organisms here, A. hydrophila is here. So the MIC of this corresponds to somewhere close to 60 ppt. So the MIC of turmeric against A. hydrophila in an ethanol extract, that is more important. In an ethanol extract, turmeric against A. hydrophila has an MIC of close to 60 ppt. So now we look at the graph for a hexane extract. So this is the graph for hexane extract. The same condition for A. hydrophila, you have the minimum inhibitory concentration as somewhere close to 500 ppt. So as you remember from the previous slide, for ethanol extract it is only 60 ppt, whereas in case of hexane extract it is 500 ppt. So as you can see here, the kind of solvent that you use to take out the exact same compounds from the source will have a different effect on the MIC concentration as well. So in this case, the hexane extract has a higher MIC, whereas the ethanol extract has a lower MIC, which means that against the same organism, if you have two different kind of drugs given and one drug has a lower MIC, it means that that drug is more potent. That is, if you have a more stronger poison, you will have only small amount of doses required. Whereas if you have a weaker poison, you will have high amount of doses required. So since MIC in ethanol extract is less than that of MIC in hexane extract, the turmeric extract in ethanol is more potent. So the main difference between the previous question and the current question is that in the previous question your drug is the same. It is the only difference in the microorganisms. So accordingly, lower MIC means sensitive, higher MIC means resistant. That is for the microorganism. Here, in this question, microorganism is the same, but the drug, that is the solvent used in the drug, is different. So you're using a different. You can basically consider them as two different drugs in case. In fact, so when you have two different drugs, the one with the lower MIC is more potent. The one with the higher MIC is less potent. So there are two different conditions we have looked at. So the answer here is option A. That is in the sorry, just a minute. So the answer here is option B. Sorry, ethanol extract is more potent than the hexane extract. So hope this is clear. The concept of MIC. MIC when you use on microorganisms means slightly different, and the MIC when you use to describe a drug is slightly different. But the entire concept is same. So it's basically logic is that the minimum amount of dose required to prevent the visible growth of microorganisms is the MIC. So based on what is asked, you can apply the logic of MIC and figure out which drug is more potent or which microorganism is more sensitive. Question 14. Mrs. Kaibartha is a fisherwoman from Mednipur. She wants to start her business of shrimps delivery to a nearby educational institutes to meet the increasing needs of her family, for which she needs an antimicrobial to enhance the shelf life of the shrimps against A. hydrophila. So based on the above results, which of the following sequence of ingredients or additives would you suggest to Mrs. Kaibartha to adopt, starting with the one which she should use in terms of cost effectiveness, health prospect and acceptability? So since from this for this particular question you need to take into the answers that you obtained from the previous question as well. So in this case she wants to use an antimicrobial against A. hydrophila, and based on the kind since she's a fisherwoman and she needs a much more cost effective antimicrobial, we need to figure out the most preferred ingredients, the preferred ingredients based on their cost effectiveness, their health prospect as well as their acceptability. So in this case you have propionic acid, sorbic acid and benzoic acid coming into picture, or you have hexane extract of turmeric, ethanol extract of turmeric and turmeric powder. So based on the cost effectiveness, since she is a fisherwoman, which one should be more preferable for her to start with at least? Based on the previous question's answers, we know that turmeric powder is an antimicrobial compound. So, since she is looking for a cost-effective antimicrobial, she can start with using a turmeric powder because of multiple reasons. First thing is it is easily available, it is cost-effective, it can be used as a part of an ingredient to her food itself directly, and she does not require any regulatory approval or anything of that sort to use turmeric powder. So when she starts her business, turmeric powder will be a good way to start using an antimicrobial, which will have both cost effectiveness, health prospect as well as acceptability. So turmeric powder should be her first preference. So after a while, if she is able to have a better business and she is able to spend more, then she should go for an ethanol extract of turmeric, because in the previous question we found that ethanol extract of turmeric is more potent or better antimicrobial activity than the hexane extract. So her second preference should be ethanol extract and third should be hexane extract, because when compared with ethanol and hexane, it is easier for ethanol to be accepted as an antimicrobial compound than the hexane. Hexane is found to be much less preferred than the ethanol. So according to preference basis, she has to go first with turmeric powder because it is an ingredient. It does not require any legal approval and is easily available. So once she is able to set up her business, she can go for an ethanol extract, which is a highly potent additive, and it is more potent than hexane extract. So ethanol is less toxic than the hexane, and hexane is actually also carcinogenic in some cases. So it is more preferred to use ethanol extract over hexane extract. So and propionic acid, sorbic acid, benzoic acid are all chemical antimicrobials, and hence for a person who is just starting off a business and fisherwoman, this might require legal approval as well, and you have only certain concentration to which you can add these acids. You can't add acid as much as you want. So you'll have regulatory approval also coming in these cases, and hence propionic acid, sorbic acid, and benzoic acid should not be used as much as possible. So the answer to this question is option D. I hope this is clear. Any doubts so far? Any question that needs to be repeated, you can kindly let me know. Okay, moving on to question 15. What is in general the operating temperatures of a UHT process for milk? So you have 100 to 121 degrees Celsius, 121 to 135 degrees Celsius, 130 to 170, and 170 to 200. So any clue what the answer is? So in aseptic commercial sterilization, 130 to 170 degrees Celsius is the temperature condition that is used for a UHT process. And since we are using extremely high temperatures, we stick with short residence times or short duration in which you will hold the milk. That is short exposure time. So if you go for higher temperatures, the amount of time you need to expose the milk to such higher temperatures will reduce. So this is one of the crucial parameters of a UHT process, where you expose the food product to very high temperatures but for very short time. So the answer is option C. Moving to question 16. Which of the following statement correctly states the definition of aseptic processing? A. Heating the food after it has been placed in the container. B. Heating the food and immediately packaging it aseptically. C. Heating the food and then packaging it aseptically followed by cooling. D. Heating and cooling the food and then packaging it aseptically. So in this case, as I had mentioned before in the previous one of the questions, aseptic processing involves either heating the food separately, heating the container separately and then packaging it aseptically, or you put it in the container and then you can follow an aseptic processing as well. In this case, aseptic processing, generally what we do is, instead of placing it within the container itself, most preferred way is to heat and cool the food. That is, heating and cooling the food will sterilize the food, or will process the aseptic processing of the food will happen by heating and cooling. Then you will have the aseptic container as well, and these will be packaged in an aseptic condition as well. So everything needs to be maintained in a sterile condition for the entire process of aseptic packaging. So the answer is option D. Moving to question 17. Which of the following two are the most important factors that provide commercial sterility to a food product? A. Temperature and pH. B. Temperature and solid concentration. C. Water activity and solid concentration. D. Water activity and pH. So in this case, in most commercially sterile food products, temperature and pH are regulated for achieving higher shelf life. So if you have a very high, if you process the food at very high temperatures, you often have the ability to even kill the microorganisms. And pH, if you regulate the pH, it will automatically disrupt the internal environment of the microorganisms. That is, it will affect your cytoplasmic pH, it will affect the enzymes, it will affect the proteins inside the microorganisms, and hence this will prevent the growth of microorganisms as well. So temperature and pH are the most commonly used factors and most importantly used factors for commercial sterility of the food product. So the answer is option A. Moving to question 18, the PUFA or polyunsaturated fatty acids in natural and virgin triglycerides exhibit A. cis geometry, B. trans geometry, C. both A and B, and D. none of these. So here you can see this is not an example of polyunsaturated fatty acid. This is an example of monounsaturated fatty acid. This is because you have only one double bond here in the entire molecule. If you had multiple double bonds in the molecule, then you can call it as polyunsaturated fatty acids. So in this case, this is an example of a monounsaturated fatty acids. This is just to show you how a cis and trans fatty acid would look like. So the cis fatty acids, you will have the hydrogen molecules on either sides of the double bond facing in the same direction. And the trans fatty acids, you will have the hydrogen bonds on the either side of the double bond facing in the opposite direction. So apart from this, here you can see something that is most obvious is that the cis fatty acid, you can see a kink here. That is, on this side of the double bond, your molecule is straight, whereas on this side of the double bond is kinked and the direction or the orientation has changed. Whereas in case of a trans fatty acid, the kink is not that obvious. That is, so for cis fatty acid, you have a higher kink, and whereas in case of trans fatty acid, you have a smaller kink. So this will actually affect a lot of things. I will explain you soon. So in polyunsaturated fatty acids, naturally they are present as cis geometry. That is, they are present in this manner. As upon heating, they are converted into trans fatty acids. Now, trans fatty acids are not preferred for one of the main reason is that because of the kink. So in case, as you can see here, trans fatty acids has a very small kink, which means that it will be able to pack against each other very efficiently. Whereas in case of cis fatty acid, because of the kink, many other fatty acids will not be able to come together and pack that well as a trans fatty acid. So just to explain better, since there is no kink here, you will have multiple fatty acids coming together and packing against each other. Whereas in case of a cis fatty acids, because of the kink, two fatty acid molecules cannot come as close together as possible, and hence the packing density will be reduced for cis fatty acids. Because of this, cis fatty acids have a lower melting temperature than compared to the trans fatty acids, because trans fatty acids have a much denser packing than the cis fatty acids. And because of this denser packing, that is one of the reasons why health-wise trans fatty acid is not preferred, because of this high packing ability of the trans fatty acids. This can often form plaques inside your blood vessels and further help in further result in blocking of the arteries or your blood vessels, which is why trans fatty acids is not preferred. That is one of the other reasons why you don't keep reheating your oils, because this will increase the amount of trans fatty acids as well, and this will cause health issues later on. This is one of the reasons why you shouldn't keep on heating your oil. And so naturally present, your triglycerides or your oil will have a cis geometry, whereas upon heating this will be converted into trans geometry. So the answer is option A. Moving to question 19, which of the following is found only in animals? A. Steroids, B. Terpenes, C. Cholesterol, and D. Phytosterols. So these four are different kinds of lipid molecules. We will discuss one by one. So sterols are derivative of steroids and are found commonly in all eukaryotic cells. So they include both animals as well as plants. So terpenes are lipids that are composed of 2 or more 5-carbon isoprene units and are also present in both the plants as well as animals. C. Cholesterol is a kind of a lipid molecule that is present only in animals. Whereas phytosterols is a structurally related compound to cholesterol. That is, the backbone of the cholesterol and the phytosterol is the same. Only thing that differs is the side chain. So phytosterols are present in uh, vegetable oils and plant-based compounds, whereas cholesterol is present in animals. So the answer is option C. Moving to question 20 and the last question. Which of the following can be used as a physico-chemical hurdle to preserve food under hurdle technology? A. You have aseptic packaging. B. Ionic radiation. C. Low redox potential. And D. Modified atmosphere. So you have multiple hurdles, and these hurdles can be classified based on whether they are strictly physical hurdles or they are physico-chemical hurdles. So aseptic packaging, ionic radiation, modified atmosphere are all physical hurdles. That is, in case of an aseptic packaging, you have multiple physical barriers. That is, you'll have a barrier for oxygen, you'll have a barrier for moisture, and then you'll have a barrier for microbe penetration as well. So because of these physical barriers, you'll have aseptic packaging, and both ionic radiation, modified atmosphere, these are all physical uh, factors that you are giving. In case of ionic radiation, you are passing in gamma radiation or so. In case of modified atmosphere, you are either changing the humidity of the condition or so, and these are all constitute as the physical hurdles to preserving the food, whereas the low redox potential comes under the physico-chemical hurdles. And basically, depending upon the kind of food that you are dealing with, the redox potential is extremely important. Let's say for a microorganism that is aerobic in nature, it requires a more oxidizing environment. That is, it requires very high redox potential. So, whereas in case of anaerobic microorganisms, it requires very low redox potential. So, the kind of microorganisms that you are dealing with highly tells what kind of redox potential should be maintained in the food. So, this depends upon this constitutes as physico-chemical hurdles and not as physical hurdles. So, the answer is option C. Redox potential is one of the physico-chemical hurdles that is used to preserve food in hurdle technology. So with that, we wind up today's session. I apologize for preponing the classes. I'm sure it would have been at the last moment, but we'll make sure that the next week onwards, we'll stick to the Saturday session as much as possible. So if you guys have any doubts in any of the questions discussed in this week's lecture, you can either mail me or post it in the discussion forum. We can take it up later. And if you guys have any doubts also, you can ask.